Welcome to the Chomp Man Games Without Code tutorial series. In this video, we'll set up our basic lighting. We'll use a mixture of baked and dynamic lighting by using a combination of light and reflection probes, HDRI, baked light maps, as well as real-time lighting. To begin, we'll first make the maze stage elements in our scene static. This tells Unity these objects won't be moved during gameplay and that they can be light mapped. Select Maze 01, the parent object to the Maze Mesh prefabs, and in the inspector, click the Static checkbox. You'll then be prompted by Unity if you want to make all the game objects static as well. We do, so click Yes, Change Children. We can now see that our Maze 01 game object, as well as all the stage prefabs under it, are now set to static. To avoid confusion, we've established a naming convention for this project. So we're going to rename the camera as such, and rename it to camera_main. We're also going to set the camera to render with deferred lighting. So under the rendering path setting of the camera, select the dropdown and choose deferred lighting. If you get a warning message at the bottom of your camera component, simply uncheck Allow MSAA. Since we'll be using anti-aliasing in our post-processing stack, we'll still have the ability to enable anti-aliasing even using deferred lighting. We also want to change our camera's background color to a darker color or black. So in your clear flag camera settings, change the skybox to solid color and adjust the background color to a dark color or black. We'll also adjust our camera's position and field of view to better reflect how it will be positioned during gameplay, or simply adjust the camera to a position that you are happy with and displays the complete maze to the player. Next, we'll adjust the lighting for our scene. Since we'll be using an HDRI skybox to establish our base scene's lighting and color, we'll need to first set that up in our scene before adjusting or adding any additional lights in our scene. Under the HDR subfolder, you should find an image called HDRI Training Stage. Select the image and inside the inspector, change the texture shape from 2D to cube, then click Apply. Once Unity has finished converting our image, you should now see a sphere in the inspector when you select the HDRI texture. Next, right-click in the project folder and create a new material. Rename the material, and in the material setting in the inspector, click the Shader drop-down tab and change that material shader from Standard to Skybox Cube Map. Drag the HDRI texture into the empty Cube Map section of the new material. Next, go to the Lighting tab. If your Lighting tab isn't displayed in the inspector, click the Windows drop-down, then find and select Lighting. In the Lighting tab, find Skybox material, then drag the HDRI material into the Skybox material. Something to be aware of, you can toggle the show lighting as well as the Skybox background in your scene view. If your scene is or begins to move slowly within the editor, toggling the lights and Skybox off can improve performance. Additionally, unchecking the Auto-Generate Lighting checkbox will also greatly improve your scene's performance. Next, we'll add both light probes and reflection probes in order to better calculate the lighting and reflections in our scene. To do this, under the Game Object dropdown in the Lighting menu, near the bottom, you'll see both light and reflection probes. We'll add our light probes first, so click Light Probes to add them to your scene. Align the light probes so that the bottom falls just below the ground plane and the top rises slightly above the maze mesh. In order for Unity to be able to use the light probes to better calculate the lighting in your scene, you'll need to duplicate and spread the light probes throughout your scene. When you duplicate the light probe group game object, you should see a set of lines connecting the duplicated light probes to the other probes throughout your scene. This is done to show that despite the fact the light probes are separate game objects, Unity will use all the light probes in your scene to help better calculate the scene's lighting. That said, the ideal way to duplicate light probes is to first click the Edit Light Probes button and keep them all on a single game object. If you're having trouble selecting your light probes, even with Edit Light Probe selected, save your scene layout and return your layout to default. You can both save and choose scene layouts by clicking the Layout dropdown, which is located in the upper right-hand section of your Unity menu. In Edit Light Probe mode, you should now notice that by selecting and duplicating your light probes, the newly created duplicate probes are still a part of the same game object. At this point, we can now duplicate and arrange our light probes, equally spacing them out until they fill our maze. Now that all of our light probes are added and properly placed, we can now add our reflection probes. To do this, click the Game Object dropdown and under Lighting, click Reflection Probe. Reflection probes capture a spherical view of its surroundings in all directions. The captured image is then stored as a cube map that can be used by objects with reflective materials. Since the sphere of the reflection probe represents where the reflections are initially cast, we'll need to move it to ensure that it's positioned high enough that it can view all the elements of our scene. We can also use the Edit Reflection Probe button to manually adjust the importance area of our reflection. Adjust the reflection probe area box so that the bottom is just below the bottom of our stage plane, the top is slightly higher than our maze height, and the sides fit the size of our maze play area. We can also offset the position of the reflective casting sphere in comparison to its position with the rest of the box by adjusting its box offset in the inspector. Now that our reflection probe and borders are properly positioned, we can now adjust its component parameters. So it isn't trying to render too much, adjust the far clipping plane from 1000 to 80 and the near from 0.3 to 0.1. Just like with our camera, this will help increase the accuracy of our reflections. Next, adjust the shadow distance to 80. With reflection probes, we have the options to use either a box or spherical reflection. By adjusting the reflection probe's intensity, we can adjust the influence it has on the reflective surfaces in our scene. Next, duplicate the reflection probe and move the duplicate so that it appears higher than the original. Then, adjust the borders so that they are surrounding the maze. Since there will be moving objects in our scene, and since our lighting is set to both real-time and dynamic, we'll use this duplicate reflection probe to cast real-time reflections. With the duplicate selected, in the inspector, change the type from baked to real-time. In order to have only minimal impact on our game's performance, we need to decrease the resolution of our probe. Change the resolution from 128 to 32. Additionally, we'll also need to adjust our far clipping plane as well as our shadow distance. If we temporarily increase our probe's resolution, we can see exactly how high our far and shadow distance needs to be in order to capture all the reflections of our scene. Adjust the far down to 15 and the shadow distance to 40. We can also adjust the probe's intensity to 0.8 so that it's not making our reflective surfaces too bright. Lastly, we'll adjust the importance of our baked reflection probe to 2 to ensure its reflections have priority over our real-time reflection probe. To keep with our naming convention, we'll also rename our baked probe to Reflection Probe Baked and rename the other probe to Reflection Probe Real-Time. For our final step, we'll bake our light map. For those unfamiliar, creating and baking a light map is a process of saving your static lighting to a texture. This not only improves your game's performance, but also improves the accuracy of lights and shadows. For the best results when creating and texturing models, create a second set of UVs to establish how your lighting should be displayed on static meshes. To know if a model has a set of Lightmap UVs, by selecting the mesh in the inspector, you will see at the bottom of the display UV and UV2. If you created, downloaded, or purchased a model that is going to be static and doesn't have a set of Lightmap UVs, Unity does have a feature that can automatically generate this second Lightmap UV set. That said, for the best result, generating them inside of your 3D authoring package will give you far more control and allow you to create smaller light maps with less seams. With that said, depending on which version of Unity you are currently using, your lighting setting may appear different. However, unless you're using the lightweight or HDRI pipeline, these settings we're adjusting should be included in your version of Unity. The first thing we want to change is our environment lighting. Change the ambient mode from real-time to baked. Next, we'll change the environment reflections from sky map to custom, and we'll use our baked reflection probe as our cube map. You can find the baked reflection probe in the scenes folder in the level 01 subfolder. After placing in our reflection probe, we'll change our baked global illumination to baked indirect. Finally, we'll check both our ambient occlusion and final gather. Since this won't be our final light bake, and the amount of final gather rays has an impact on the time it will take to generate a light map, we'll lower the amount of final gather rays to 64. We'll also increase our light map size to 2048. The light map size essentially determines the size of the texture that Unity generates for your light map, not so much the quality of the light map itself. With all of our settings in place and with the auto-generate lighting unchecked, click Generate Lighting. You can find the light map progress bar at the bottom right of the Unity interface. Depending on the power of your computer and the settings for the quality of your light map, generating a light map can take a few seconds to several minutes. If you're following along, you may want to pause the video now and start it again once your bake is complete. Once the light map is complete, by clicking the Global Maps tab in your Lighting tab, it should allow you to view the light maps for your scene. Additionally, your light maps can also be found in the same folder as your saved scene. They will automatically be placed under a folder of that scene's name. So in this case, they will be under the Level 01 subfolder of the Scenes folder. Before we end this video, let's first organize our scene. Create an empty game object and name it Cameras, Lights, Probes. Drag the main camera and directional light into the objects in the hierarchy. Next, create another empty game object named Probes and place the light and reflection probes into it. Make sure that the Probes game object is a child of the Cameras, Lights, Probes game object. That completes our level light setup. Be sure to join us in the next video where we'll continue building our Chomp Man game. Don't forget to subscribe and hit that notification bell to be the first to see this and many other tutorials, game development tips, and free game asset giveaways.